So that was SARSA, the on-policy version of Q Learning, meaning that we learn Q values for a specific policy that we are following, right? We need to somehow commit to the action in the next state. And now let's see the off-policy version of TD Learning. So this is more similar to the Q value policy iteration that we've seen before, right? It does not depend on a specific policy that we're taking. And this just follows the Bellman update, where we do take the max overall possible actions in the next state. Now you might ask, so why even consider SARSA? So I'll show you in a second an issue with off-policy TD learning. And then we'll also see a solution for that, but wait for 1 minute. Okay, so we're going to use the original temporal difference update rule, the original TD update rule, the original Bellman equation. And now we're going to approximate the state action value for the optimal policy at the next state. So we're going to approximate Q star for the next state instead of assuming a specific action or a specific policy. And again, we need to still assume that every state action pair is visited infinitely often. And then we are also guaranteed, if we just perform these updates over and over and over again, we are also guaranteed to converge on the Q star values eventually, which imply the optimal solution, right? And the proof follows from the proof of convergence for the Bellman function. We saw that in slides 25 and 26 in our third slide deck. Not only that, but it also follows from the proof that doing a Bellman update based on a single sample is unbiased, right? If you do it sufficient enough times, and we've seen that, I don't remember now in what deck, but we also saw that, I think in this slide deck, right, when we discussed it earlier, that a single Bellman update, sample-based Bellman update, is an unbiased estimation of the full Bellman update equation. Okay, so let's see an example of how Q Learning, online Q Learning, which is off policy, would work in practice. So again, going back to the same example that we've seen before, actually, maybe we switched the two terminal states, the rewards there, but in essence, it is the same example. So again, Varav, can you take us through this this running example?
So just like before, we have an arbitrarily initialized Q function. Down here you can see our domain and what our transitions in this episode will look like. Starting from state S, we take action null, receive reward null, and receive. That was initially. That's not the actual act. So we initialize our
current
position, and then we take action right. We receive reward 0 and read state Y, the new state as Y. So if you remember, for SARSA, we also had to select what was the action for the given the next state. But in this case, that action A is not sampled from the policy. We're trying to use a function approximator to approximate what would be the best max action for the new state Y. So in this case,
so we update it to 0.
Yeah.
Right.
Because our current estimate of the max action, the max Q value for state Y is 0.
Yeah, so we move to the next state.
Yeah, we move to the next state Y, and we see what action we take there. Take action right, receive reward 0, and now we go to state Z. So again, for state Z, our Q values for all the actions were 0. So we get a Q value of 0 for state Y action right in this transition as well. Finally, we reach the terminal state Z. we take action exit, we receive a reward minus 100.
So now we update that.
Yes, this updates our Z
So
value.
let's start a new episode and see what happens.
Now when we start the new episode again from state X, again nothing happens to the Q value for the actions in state X because its next state Y has 0 values for all its actions.
Continue.
And now for state Y, when we do it, since going to state Z has a minus 100 Q value, now we get a action right to state Y value minus 90.
Y minus 90?
Because of the discounted
we have a
future
discount
rewards.
factor, right.
Yes.
Okay.
So we have gamma of 0.9 that discounts our future rewards. And then now we start a new episode, finally, this time when we take an action from state X.
So 1 second. So you're in state X and again you're following the same policy,
Yes.
going right.
So this is our third episode, starting from state X.
So what will happen now? The immediate reward will be 0 and you'll get to state Y.
Yes.
So how will you update X right?
So right now X would still be 0, but once
there's a minus 90 in Y.
because the value of the max action reward in state Y is now left, which is 0, has a Q value of 0. So if you were to update the Q value for state X action right, it would go to state Y and take action left, since we're taking the max action.
Right. So unlike in Sarsa, here we don't commit to a specific action. We're not saying from Y will always go towards Z.
Mm-hmm.
But we're looking at the highest Q value. So from X, we did go right and arrived at Y. But now we say, well, at Y, the optimal policy will not go right? That's a minus 90. Currently, the best we can do is actually go back left, which has a Q value of 0. And that's what we're going to use to do the update. Right? This is why it's off policy. It doesn't matter if later on we would take right in Y. We won't use it for the update. Right? It's off policy. The policy that we use to interact with the environment is not the one that we learn the Q values for. We're trying to learn Q stuff. Okay, thank you. Good job.